Hello everyone. Today we will be discussing about an example of the transfer function. Like in the last lecture, we discussed about the what is transfer function and how the transfer function is calculated and why it's required. So, if you haven't watched that video lecture, or if you don't have any idea about what is the transfer function is, I would request you to go watch that video or any video regarding the transfer function from any channel, or get some idea from the book, because here I will be explaining a little bit about one example. So what is the topic is example on transfer function. So we'll be taking one basic example, like which is the most basic uh, system for a control engineer, or like a secondary system. So from the mechanical engineering point of view, like spring, mass, and damper system. Similar equivalent of electrical engineering, electrical guys, is the RLC, resistive, inductive, and capacitive circuit. So these are the basic second order systems. So basic secondary systems. So uh, like what is the second order, what is the first order, third order, that I will be explaining in the future lectures. But just know, because the system dynamics has a second derivative, that's why it's called a second order system. So the spring mass damper system is like, if this is some rigid wall or floor, you can say. This is a spring, this is a damper. I guess you might be having some idea on what is the spring mass damper system. I'm assuming that. And these are the spring coefficient is spring constant is K, and the damping coefficient is C, and M is the mass of the small m. Small m is the mass of the system, and what we want is like if we apply some force U, we are stretching, we are pulling the mass with some force U, which is the some force, the control input, and if we assume this as the reference point or 0 point, so like when the spring is unstretched or uncompressed, this is the natural equilibrium point, this line. So from any deviation from this, it's called y is the displacement or the position. So this is our output. Okay, this is our input. So from the second order dynamic equation, we can get the following equation. Like you might be knowing about it. The the equation of motion is defined by the expression m into y double dot, which is the acceleration, plus c into y. Just let me denote the time dependency. C into y dot of t plus k into y of t is equal to b of t. So basic force balance expression, it's an equation of motion. So I am assuming you are well versed with the expression or the equation. I'm not deriving it. It will be taking bit more time. So I'm assuming you are well versed with the expression. So what our transfer function mm, definition says the Laplace transform of the output divided by the Laplace transform of the input. So let's take the Laplace transform. So Laplace transform of m of y double dot of t plus c of y dot of t plus k of y of t is equal to Laplace transform of u of t. So I know, like, just remember, try to remember what I had mentioned. Like, m is like here, we're assuming m, c, and k are the constants. So m into Laplace of y double dot of t plus c of Laplace of y dot of t plus k of Laplace of y of t is equal to Laplace of u of t. So as we know, like, what is the Laplace transformation of second derivative? It will be s square into capital Y of s minus s into uh, y of 0, y dot, it's y of 0 minus y dot of at 0 plus c into, this is whole, and into c into s into y of s minus s of, sorry, minus y of 0 plus k into y of s is equal to u of s. So according to our previous assumptions, what we had taken is we will take like the all the assuming all the initial conditions to be 0. Like here you can imagine, like when where time is starting, we had mentioned this is at 0, and what does the this term y dot of 0 defines at the at time 0? What is its velocity towards this or towards this? No, but we are assuming this is like this is at a constant like it's constant, it's not moving at all, so it doesn't have any velocity. So you can say before time, like the force is applied, y dot at 0 is equal to 0. So that's why we're taking this as 0 and this as 0 and this as 0. So ultimately what we got, m into s square of y of s plus c into s into y of s plus k into y of s is equal to u of s. Dividing it, what we will get, y of s by u of s is equal to 1 by m into s square plus cs plus k. So this is called second order transfer function. Second order transfer function. So you can see this is the, due to this s square term, this is called the highest degree of the denominator is s square, which came from the this term like y double dot. So it's called a second order transform function. So let's take an example like from in MATLAB. Uh, let's assume m is equal to some value 1, maybe c is equal to 3, or k is equal to 5 maybe. So what my expression will be, then tf is equal to 1 by s square plus 3s plus 5. So this expression like will be like the input what we'll take is one is step input and maybe the other one is sinusoidal input. So we'll see how the responses are, how the system behaves when the inputs are step and sinusoidal. So in MATLAB, so switching to the MATLAB window. So we have switched to the MATLAB window right now. So you can see the MATLAB window here. Here is the command window, and here is the current folder. I currently don't have any functions or any MATLAB file in the folder. And here is the workspace where we can see all the variables we create. Okay. So you already know, I guess you already know the basics of MATLAB, like what is this home window, and this is the script, how the script look like. Here I have opened the editor, where here we will be writing out the codes for it. So it's a, like, I recommend you all, first one, whenever you open a new script, like new editor, first save it, so that whatever you write, it gets automatically backed up. uh, so when something wrong happens, your computer shutdowns or some problem happens, the program is still there, otherwise you will be losing your program. So I will be naming it as transfer function example. Okay. So the I prefer writing the code in different sections, like the mm, double percentage gives the different sections, so that it's easier to run the different sections, and then like to debug the code. It's always helpful. Like, I personally find it helpful. That's why I always do this. So this is a transfer function example. So I recommend you always, when you start a MATLAB program, just use these three commands: CLC, clear, closure. What it does is, the CLC command clears out our command window. Like, if you already have something in your command window, the command window is cluttered, then it just clears it. Now you can see the clean command window. So if it was not clean, then the CLC command will be cleaning that. And the clear will be clearing the workspace, whatever the memory are allocated to some variables, and all the variables, it just releases all of them. And close all, what it does is, it closes all the different windows, like the MATLAB windows. Like when you put some figure, or put some other window, or put some Excel file, so close all will be closing all the remaining files. Just keep this window. Okay. So I delete this space. Okay. Then here we'll be defining the constants for the system. Another thing is that I always recommend you to write out the comments, so that when someone else is reading out your code, or trying to understand the code, they will be getting the idea. Like here, if I write m is equal to whatever we had taken, the mass is equal to 1, and maybe c is equal to 3, and k is equal to 5. So now you know, like here we are defining the constants for the system. If I hadn't mentioned it, you might be getting the idea, like why, what are this, but somebody might not get the idea. So it's a good practice if you comment everything. And even when you look at the code after couple of months, or maybe after a year, then it's easier for you to get it understand. So now we'll be creating the transfer function. Creating the transfer function. The transfer function, what we have currently, like the g of s is equal to 1 upon s to the power s square plus 3 into s plus 5. Is it correct? Yeah, it's correct. So what I will be doing is, I will be defining two different variables, one for the numerator and one for the denominator, so that when we write the transfer function it's easier for us. So the numerator is equal to 1, it just have 1, and g is then is equal to, what are the coefficients? I only need the coefficients. Coefficients are m into c and k. So what it will do, like why we are writing like this, I'll just explain. Let me write the complete transfer function. It's the df of g underscore now and g underscore then. So what it will do, the tf transfer, like this tf, the function tf, the predefined function tf, what it will do, it will take this, the first variable as the numerator, which is 1, and second variable as the denominator, and what it will do is it will multiply s to the power s power 0 1, like from right to left, like it will multiply k with s to the power 0, c with s to the power 1, m with s to the power 2, like that. Like you can always check help tf. So this is a very beautiful command of MATLAB command window. Like whatever you face problem, you just type help tf, it will give the documentation. I'll just make it big. So the system will be the tf of numerator and denominator, and the denominator you will just see. Okay, you can go through it. I won't be going deep into like in details because it will take a lot of time. So let's see how okay, now we'll just clean. You saw like the CLC, it just cleans all the things that were in the command window. And now when we run it, like the beautiful thing about the section is you can run individual sections from the run section. That's why I prefer it. So here we have created three variables, m, c and k, and they are the values what we have defined. And coming to g, now when we run it, we have created another variable called gnum, gden, and g, there is a block. So when we type what g is, we can see g is 1 by s square plus 3s plus 5. So what exactly what we wanted, correct? So now my question is, if I write I want to write function like the transfer function g2, maybe g2 is equal to 1 upon, sorry, I will write s upon s to the power 3 plus 3s. Okay, so then how will we write? Can you guess it? I'll just write it down so that if you have guessed it correctly, then that's great. I'll directly write in the command window g2 is equal to, yes. So in the now the numerator also has, it doesn't have 1 anymore, it has s. So in this we have to define what is the power of s, it's 1, and what is the power s to the power 0, the coefficient of s to the power 0, it's 0, correct, comma, the numerator is done, the denominator is s cube plus 0 into s square plus 3 into s plus 0 into s. So 1 space 0 space 3 space 0. I think you have understood. If haven't understood, like let me explain it again. The numerator has a power s power 1, so that's why we will be defining s to the power 1 into its coefficient, which is 1, and s to the power 0 into the coefficient 0, because s to the power 0 is absent here. If it would have been plus 2 or something, then would have been written here 2 instead of 0. Similarly for the denominator. So have we, okay, wait a minute. Okay, sorry, I haven't expressed the TF. Yeah. So now we have s upon s cube plus 3s, correct? So okay, now coming back to our transfer function. So now in taking step in sorry taking step input, it's the we'll define some figure, and the figure is step of G. So what this steps input does is like it will be giving out the step response to the function, and if we run it, you can see this is how the step response looks like from it starts from 0 and and it is settled around this. So if you want, you can also give some other command like the if you want till some time the step of G till I want till 10 seconds. Sorry, so I'll just comment this out and run it again. So you can see it has run for 10 seconds now, so you can play along with it. So now we'll be taking the sinusoid input. So for the sinusoidal input, I will be going to the Simulink because it's easier over there. You can directly write down the command Simulink over here and run it. Give it few seconds, and you will be the Simulink tab will be opened. Now you can see. So this is the Simulink window that we'll get, and so let's browse the library. It may take a little bit time to open this window. So what we are doing is we are doing the continuous time. So here in the continuous time, you will have different options like derivative, descriptor, state space. Here you can find a block called transfer function. So you can right click it and just a second, sorry. Here add to model untitled, the untitled, like this is the, we haven't named the Simulink model yet, that's why it's showing untitled. So as we have so after minimizing it, you can see it's only the 1 by s plus 1, but we want to modify it according to our coefficients. So the denominator coefficients are 1, 3 and 5 for our case. So apply. So you will be having some numerator and denominator, whatever we are having now. Then you need another like scope. Like scope is nothing but just you can search scope. It will show us the plot. Like it's a tool that is useful to visualize the plot. Like in MATLAB, you had defined the figure, right? So like that, there is a scope. So this is the scope. You should add it to untitled. Move it like this. Now let's step input. You can search anything here, so you can get the step like this. This is the step input. Now connect the wires from here to just drag and drop it on the window. Now if I run it, before that I should save the Simulink file. So this, just remember Simulink extension is slx.slx. So tf example. So I have saved it. Okay, now run it. So it's the runtime we have given at 10. So in the scope, you can see the step response, like it's the exact waveform we had got in our normal MATLAB script. So now what we will do, instead of step signal, we'll give the sinusoidal input and check what is the output. So I will type just sine. So some sine wave, this is the sine wave, like, and add it to, now you can see as we have modified the name, it's tf example, and this I will disconnect this, I will just delete this one, and I will join this to this. Okay, so what happens when we provide a sinusoidal input? So my result is ready. You can see, like if I give the sinusoidal input, the property, the same sinusoidal input is the output with some magnitude difference. And what is the magnitude difference? We can check. 1 second. The input sine wave had magnitude of amplitude 1, but the output has a magnitude of 0.2. So, and it's the property of sine wave is preserved, like if as it's a linear system, I have explained that thing in the previous lectures regarding, no, so like if the input is a sine wave, then the output will also be a sine wave, just with the phase difference and amplitude amplified or reduced. Okay, so now we have got in this lecture the summary of the transfer functions and MATLAB and Simulink. So we'll meet in the next lecture. Thank you.